Hello everybody, my name is Timid Actor. This is my Project 1 video for control systems on convolution response. And going right into it, as the title says, the main focus of this project is to understand the concept of convolution and the systems by mathematical derivation as well as real-world application. My initial goal when I saw this project was to think about understanding how a system works in response to an input signal x of t, first through sampling and it's taking its pulse approximation, and then applying that same idea to the second part of the project, which is dealing with real-world recordings, taking audio recordings and having an environment as our system. And I just pretty much said it. Part 1 focuses on the mathematical foundation that we need to use pulse sampling to show the convolution integral. And part 2 is applying those same concepts to real sounds and recordings and show how convolution works in the physical world. Both via MATLAB. Now, let's start with talking about the linear time invariant, or LTI systems. And LTI systems have two main properties, which include the superposition and time invariance. Superposition, in my opinion, is pretty simple. It means if we have, say for example, we have an one input, which is x of t, or x1 of t, and its output is y1 of t, and we have another, its output is y2 of t. We can sum, if we were to sum up the inputs, it would be the same as summing up their outputs. So x1 of t plus y2, x2 of t, y1 of t plus y2 of t. Now moving on to time invariance. Time invariance means if we have an input signal and we were to shift it in time, the output signal would also be shifted by that same amount. And using these properties, we can represent any signal as smaller shifted signals, and then summing up their responses, that would give us the system's total output or original signal. Continuous signal x of t. We'll get more into the one I chose. But if we were to take that x of t and sample its pulses, and each pulse is a small piece of this signal, and we were to add them up, sum them all up, we would get an approximation of this original waveform. And seeing this convolution integral right here, which essentially says as delta gets smaller, we use more and more pulses under this curve, and these tiny pulses turn into the convolution integral, which as it approaches 0 is pretty accurate to what this original signal is. And now moving on to part 1, where the MATLAB starts. Now, the input signal I use is x of t is equal to e to the minus 2t cosine 3 pi t. This is both an exponential decaying and oscillating sinusoidal waveform function. Go over to the MATLAB. We can see on the top left, right here, I already did the outputs of my code. If continuous, and the other 3 show different delta conditions, different pulse widths. So the first one is delta of 0.25, then we have 0.1, and then 0.01. And what you can notice is that these blocks, you can tell these pulses, since their width is so large, you make out that they're blocks. They don't really look like what our original function is. And generally how I understood it, this is not going to be as our original function. But as we approach lower and lower delta, we can see in the second one where delta is width it's a little bit more accurate, but not as accurate as when we move on to 0.01, where it starts reaching that continuous integral, and to what our original signal was. So what we expected mathematically. As delta gets smaller, right here, as delta gets smaller, the discrete sum of those rectangles, those rectangular pulses, become this continuous time convolution. In other words, we just demonstrated how continuous convolution can be built up step by step, and sampling those steps to our original function. Review of part 1. Now moving on to part 2, the objective here was to take that math concept from part 1 and apply it to sound and recording. And I treated the recording environment as a system, and I used my own voice as the input signal x of t, and a hand clap, which the clap of the hands represents our response, which is h of t. The clap is how sound behaves in space, and you can hear that echo from that impulse response. And when we convolve, and we convolve my voice with the clap, the output t simulates what my voice sounds like if I were to be in the environment that this was recorded in. So this was recorded in a cleaner environment, damped, no echo. This clap was recorded in a empty room, so the echo is larger. If I were to play it, let me play it, you could hear it. Now there you can hear it. It genuinely was impossible. But yeah, as you can hear, after performing that convolution, the resulting audio, it had no, and the original voice file. Now, the new voice was, it seems as if it was recorded in the same environment or same system as where, I guess you could say, our impulse function was taking place. And this matched what I expected, and it showed how we can accurately recreate a system. It really uses the same math that we used in part 1, only this time instead of drawing it, we can actually hear it. Let's wrap up. And to generally wrap up, the project really did help my understanding of the theory of convolution and how it also works in the real world. I think actually hearing what I sounded like gave me a better understanding compared to part 1. Like part 1, I did understand where how you have a pulse sample which leads to the continuous convolution integral, and how the sum of those small responses form the system's total output. But it really reinforced it with part 2, where I experienced the same concept through sound and using those real recordings to simulate how an environment really the audio, and like how that environment in our case was a system. But yeah, overall, I learned that convolution isn't just a math formula. It's interesting on how it works on all kinds of systems. At the 10-minute mark, I might have to edit this. Wait, I'm trying. Ooh. Testing my voice for convolution response project 1. It's impossible to find my voice for quiet space. Convolution response project 1. It's impossible to find a quiet space.